finished section 3.1 where we learned what a function is and how to identify functions. Today we are jumping into section 3.2 where we will look at functions and learn how to determine if they are linear or nonlinear. So just like our 3.1 notes, you will follow along with this video and complete your Google Slides by typing what I type as you follow along in the video. So there will be 2 times throughout this video and throughout these notes where you will need to pause and spend some time completing some examples on your own and giving your answer to Ms. Zell or myself in the Zoom chat. Alright, so let's go ahead and start off with some vocabulary. So we have 3 main pieces of vocabulary today. Our first one is about a linear equation in 2 variables. So a linear equation in 2 variables, the variables being x and y, is an equation that can be written in the form y equals mx plus b, where m and b are constants, meaning the values of m and b will not change, so they are constant values. And the graph of a linear equation is a line. Notice a linear equation literally has the word line in it. That's what tells us that the graph of a linear equation will be a line. All right. So now you're asking, what is a linear equation? A linear equation is a linear function, is a function whose graph is a non-vertical line. And it's important that you keep in mind that it is a non-vertical line. And a linear function has a constant rate of change and can be represented by a linear equation in 2 variables. So just to review, a linear equation in 2 variables is an equation that can be written in the form y equals mx plus b, where b and m are constants, meaning their value will not change. And the graph of a linear equation is a line. Now, a linear function is a function whose graph is a non-vertical line. Again, it is important to know that it is a non-vertical line, because if you recall what a function is, it's when one output has exactly one output. Now, if we draw a vertical line, that automatically tells us that one output will have many outputs along that vertical line, which will no longer be a function. So it's important to remember that a linear function is a non-vertical line. All right? And a linear function has a constant rate of change and can be represented by a linear equation in 2 variables. Lastly, a nonlinear function does not have a constant rate of change, so its graph is not linear. You may be wondering, what is a constant rate of change? It is what you explored with your group earlier today in that 3.2 exploration, but we will be getting into the constant rate of change when we look into looking at tables. All right. So this is our vocabulary that we'll be using. We'll go ahead and look at some examples. And throughout the lesson today, we will be looking at how to identify linear functions using graphs, using tables, and using equations, which is something a little bit new in this chapter. All right, so first, let's go ahead and look at these graphs. So the question is, does the graph represent a linear or non-linear function? And we want to explain. So looking at this first graph, you guys, this is what we call a parabola. And if you notice, a parabola is a curve. So this is not a line whatsoever. So our answer is as simple as that. Looking at this graph is not a line. It is a curve. Therefore, the function is non-linear. So when it is not a line, it is non-linear. All right. Now looking at this second graph, we see that this is a pretty obvious line, and it is a pretty obvious non-vertical line. So because this graph is a line, then the function is linear. So when the graph is indeed a line, that means that function that is being graphed is a linear function. The graphs are pretty straightforward, probably the easiest way to determine if a function is linear or nonlinear. But we will go ahead and get into looking at tables. So perfect, we're going to be identifying a linear function using tables. And there's all these boxes here, guys. So when we look at tables, similar to how you just did it with your groups for the exploration, we want to observe first how the x values and the y values are changing. So we want to ask ourselves, are they changing at a constant rate? Or in other words, are they changing by the same amount each time? So let's go ahead and fill in these boxes first. So from 3 to 6, I would say we are adding 3, right? From 6 to 9, I would still say that we are adding 3. And from 9 to 12, I would still say that we are adding 3. So our x values are changing by 3 each time. Okay? Notice how it's changing by the same amount each time. That is going to be important for us as soon as we figure out how the y values are changing. Right? So from 36 to 30, I would say that y value is changing by subtracting 6. Same with 30 to 24, I would say that y value is also changing by minusing 6. And same thing with 24 to 18. I would still say that is also changing by minusing 6. So now I can go ahead and make an observation that as x, so before I make my observation, notice how the x values are changing by the same amount of plus 3 each time, and the y values are also changing by the same amount of negative 6 each time. So as x increases by positive 3, y decreases by negative 6. That means that the rate of change is constant. So the rate that x is changing and the rate that y is changing is constant every time. It is the same every time. That is what constant rate of change means, is that the x value is changing by the same amount every time, and the y value is also changing by the same amount every single time. So since the rate of change is constant, the function is linear. The function represented by the table is linear. Alright. Now let's go ahead and look at this second example. Let's go ahead and look at our x values and how they are changing each time, and same with the y values. So from 1 to 3, I would say that I am adding 2. From 3 to 5, I would still say I'm adding 2. And from 5 to 7, I would still say I'm adding 2. Notice how we are adding 2 every time, so we could be off to a good start and hopefully have a constant rate of change, but we need to check our y values first before we can determine whether it's a constant rate of change or not. So from 2 to 9, I would say that's adding 7. From 9 to 20 though, keep in mind, that's adding 11. So already we know that we don't have a constant rate of change because from 2 to 9 we're adding 7 and here we're adding 11. So this rate of change is not the same, or it's not constant. Let's go ahead and fill in this last box right here. From 20 to 35, I would say that's adding 15. So even though the x values are changing by the same amount, the y values are not. So as x increases by +2, y increases by a different amount each time. So the rate of change is not constant. So the function is non-linear. So when we do not have a constant rate of change, that means that our function is non-linear. All right. So just to let you guys, to kind of emphasize the key idea on this slide, when we are looking at a table and we notice that the x values are changing by the same amount each time, as well as the y values are changing by the same amount each time, that means we have a constant rate of change, meaning the function that is being represented is a linear function. And when we do not have a constant rate of change, the function is non-linear. All right, so moving on to this next slide, this is where you are going to pause the video and attempt to determine whether we have a constant rate of change shown in this table and if the function is linear or non-linear. Perfect. Let's go ahead and move on to identifying linear functions using equations. So our question here is, which of the following equations represent linear functions, and explain. So we have these 6 functions right here: y equals 0.38, y equals the square root of x, y equals 3 to the x power, y equals 2 over x, y equals 6 times x minus 1, and x squared minus y equals 0. So remember, guys, that if a linear equation can be written, in the form y equals mx plus b, where m and b are constants. Again, that means that they are not changing, the values are not changing. Then that linear equation represents a linear function. So we're going to keep that in mind when we are looking at these equations and determining if they represent linear functions. All right, so going to the next slide, we have these 4 equations up here: y equals square root of x, y equals 3 to the x power, y equals 2 divided by x, and x squared minus y equals 0. Notice these 4 equations up top right here are simple and written in a way that doesn't allow us to rewrite them in a new form or the form that we want. So since these equations cannot be rewritten in the form y equals mx plus b, then they cannot represent linear functions. So again, since these equations cannot be written in the form y equals mx plus b, then it's not possible for them to represent linear functions. However, keep in mind that we do have these 2 equations left over, and these can actually be rewritten in a different form, or the form that we want. So y equals 0 plus 0.38, notice that is a constant. There is no variable attached to it, so this is already a constant. So I would say that this can be rewritten as 0 times x, since 0 is a constant, and anything times 0 is 0, plus 0.38. Right? We can see this is in the form of y equals mx plus b, where this is our m, this is our b, and 0 and 0.38 are both constants. So this represents a linear function. And similarly with y equals 6 times x minus 1, we can actually use the distributive property to go ahead and distribute this 6, and that will give us 6 times x, which is 6x, and 6 times negative 1 will give us a minus 6. Keep in mind here, m equals 6 in this case, and b equals negative 6. These are both constants, meaning this is in the correct form of y equals mx plus b. So this also represents a linear function. And if this helps you that I labeled what m and b are, I can do the same thing here. So y equals 0x plus 0.38, where m equals 0 and b equals 0.38. So again, to reiterate and emphasize the key idea of using equations to identify linear functions, if we can rewrite an equation in this form, then it will represent a linear function. Just like here, we could rewrite these equations in these forms, meaning it does represent a linear function. So now it is your turn to go ahead and try this simple example. This will be your exit ticket. So does this equation represent a linear or nonlinear function? Explain. Again, you will private message your answer to your teacher in the chat.